And hello everyone, I'm Meishan, and thank you for joining today's webinar. So in the following 20 minutes, we will focus on the determination of the BET surface area with two unique techniques, the dynamic vapor sorption and the inverse gas chromatography. So these two sorption techniques are especially suitable for some low surface area materials, for example, some organic materials, some metal powder, or the crystalline material with the surface area well below 1 square meter per gram. And the sorption technique in this case will give a more accurate and reproducible result that we will go in detail later. So here's the outline of the presentation. We will first have a brief introduction about the BET surface area, and then I will introduce some basic information about the two techniques, as well as the application and the case studies related to the BET surface area determination. So first of all, from the classifications, there are 6 types of sorption isotherms based on different sorption mechanism. So the type 1 isotherm is typical for some microporous material that has relatively small external surface areas. For example, some active carbon, zeolites, or some MOFs material. So for type 1 isotherm, the limiting uptake is more dependent on the accessible macropore volume rather than the internal surface area. The type 2 and type 4 isotherm are the normal forms of the isotherm obtained with the non-porous or microporous material, with the monolayer and the multiple layer absorption of the probe molecules. And these two isotherms are the ones used for the BET calculation, where we use the monolayer region to calculate the surface area of the solid material. The type 3 and type 5 isotherm represent some weak interaction between the probe molecules and solid surface. So for example, as the water sorption isotherm is usually a type 3 isotherm. It's more like some condensation on the surface that the absorbate interaction is much stronger in the comparison to the interaction between the water molecule and the solid surface. So here is the classical equation from the BET theory, where the X is the partial pressure of the vapor above the surface, and V is the amount of vapor absorbed on the surface. So if we take the left part as the ordinate and X as the abscissa, it should give a straight line with the linear regression. And from the slope and the intercept here, we can then calculate the monolayer volume, the Vm, and the sorption constant, the C value from the line. And with the cross-sectional area of the absorbing molecules, we can then calculate the BET surface area of the solid sample itself. So it's very important to have a linear line to fit the BET model here. And that's why we need to get a type 2 or type 4 isotherm with the linear region for the monolayer sorption. So for type 2 and type 4 isotherm, the probe molecule will first interact with the surface, forming the monolayer, and then interact with the first layer, forming some multiple layers. But if there are too strong interaction between the probe molecule, they will form some clusters on the surface rather than cover the entire surface with the monolayer. So this will give the type 3 and type 5 isotherm. And this kind of probe molecule has weak interaction with the solid surface and are not suitable for the BET calculation. Therefore, we can try different probe molecules for the absorption isotherm to get the right type of isotherm for the BET determination. For example, here with the lactose sample, with less polar probe molecules, the shape of the isotherm is approaching to type 2 isotherm. So it's not recommended to use the water isotherm, which is a type 3 isotherm, for the BET calculation, but we can use some other probe molecule like butanol or propanol, and this will give a better result for BET calculation. So we have different methods for BET determination. For example, the most common method, like the volumetric method with nitrogen sorption, which is quite good for some porous material like zeolite or silicas, but the nitrogen sorption also shows some limitation in terms of the low surface area material, like the pharmaceutical powder, the hair fiber, or some carbon fiber material. And in this case, the vapor sorption technique, for example, like DPS and IGC, will give a more accurate and reproducible result. And with regard to the conditions of the experiment, the vapor sorption technique are performed at ambient temperature and pressure with the organic vapors. So the result is more close to the surface area at real-world conditions during the processing or performance with the sample. And in terms of the volumetric method, for the sample with the surface area below 1 square meter per gram, the nitrogen sorption technique will give a result with quite high deviation, like around 10% RSD, which is due to the sample is absorbing a very small quantity of gas, and this will make the size of relative error unacceptable. So in this case, we need to use krypton instead of nitrogen as the sorbate, but krypton is a quite expensive gas for use. And apart from that, the volumetric method is performed at very extreme conditions, like the liquid nitrogen temperature or the very low pressure like vacuum. And these conditions are not friendly to some sensitive or fragile materials that will collapse under these conditions. And it will also dry out some of the hydration waters during the experiment for this kind of pharmaceutical powder. So the mirror surface area with the volumetric method in this case is not the original surface of interest anymore. But with the help of vapor sorption technique, for example, the inverse gas chromatography, we can use some organic vapors at ambient temperature and pressure. So it can mirror as low as 0.1 square meter per gram surface area, still with very good reproducibility. And it's also reported in this paper as well about the effective surface area of the pharmaceutical ingredients. So it says that the surface area of these spray-dried dispersions are not accessible for the standard nitrogen sorption, while IGC method with the outgassing at ambient temperature will reduce the risk of potential change inside the sample. This means the sorption technique is more suitable to determine the surface area of those low surface area material. So we will then focus on the true sorption technique. A sorption technique is using molecules as a probe, and from the gas-solid interactions, we can get all the information of the solid material related to the chemistry, structure, as well as the thermodynamics. So the first sorption technique we will introduce today is the dynamic vapor sorption. And basically, it's a gravimetric method to measure the mass change of the sample at different concentrations of moisture or organic vapor. It has the ultra balance in the system with a very high sensitivity, and the resolution of this balance is 0.1 microgram. And the balance is connected to both the sample pan and the reference pan. And the carrier gas for the system is nitrogen or compressed air. And there are two reservoirs in the system, one for organic vapor and one for water vapor. So different concentrations of moisture or the organic vapor will be generated by the mass flow controller by mixing the carrier gas and the saturated vapor in ratio to get a certain relative humidity. And this mixture will flow to the sample chamber at a constant rate, and the sample inside the chamber will pick up the moisture, and the mass change will be recorded by the balance. So the whole stand here will sit in an incubator with the temperature range from 5 to 85 degrees. And under the sample chamber here, we can also install a preheater that allows the preconditioning of the sample up to 200 degrees. And the system can also be equipped with the camera or Raman to take the images or the spectra during the experiment, having a complete understanding of the structure change along with the sorption data. So with a typical DPS experiment, we first change the partial pressure inside the chamber, and the sample inside the chamber will pick up the moisture and then reach equilibrium. It will then jump to the next stage automatically. So the sample mass change will be recorded continuously, and this will give the kinetics information from the mass plot here. And if we plot the change of mass with the relative humidity, Then we will get the isotherm plot with the sorption and desorption cycle. And from the isotherm plot, we can then calculate different properties of this solid sample, like the surface area, the surface roughness, the porosity distribution, or the heat absorption. And with the DPS data, we can also predict some stability or the shelf life of the sample at different conditions. We can also measure the vapor-induced phase change for the glass transition temperature and the humidity. And with DPS, we can also do the diffusion or the permeability studies with the pencil in DPS instrument. And we have different previous webinar recordings online for these applications. So if you're interested, you're welcome to have a look on our website. And here I will just focus on the BET surface area determination. So for the DPS case study here, we used the lactose monohydrate sample, and we did the octane sorption at 25 degrees from 0 to 100% RH with 5% intervals. And this is the octane isotherm, which is a quite typical type 2 isotherm. And then with the BET equation in the previous slide, we can convert this isotherm into the linear BET plot. And from the slope of this line and the intercept, we can calculate the BET surface area of this lactose sample is about 0.25 square meter per gram with a very good linear regression. And this value is quite consistent with the reported value for the lactose in the literature as well. So here demonstrates the potential of DPS for the determination of low surface area materials. And the other sorption technique we will introduce is the inverse gas chromatography. And the principle of IGC is quite simple, just being opposite of the conventional gas chromatography. For example, in the traditional GC experiment, we will have a certain kind of solid as the stationary phase, and we will inject an unknown mixture of the gas compounds through the stationary phase. And there will be different peaks showing up here, giving the quality and quantity information of the injected compounds at the very beginning. And in case of inverse gas chromatography, this time we will pack the sample of interest into the column, and there will be a post-injection of single organic vapor through this column, and there will be only one peak showing up here. And from the retention time and retention volume, we can calculate the surface property of this solid sample inside the column. And this is some basic procedures for IGC experiment. So first we need to pack the sample of interest into the column, and then we select different probes for different interactions, like the non-polar probes for the van der Waals interaction and the polar probes for the other chemical interactions. And then we inject different probes at different concentrations, and from the detected signal, we can calculate the physical chemical properties of the solid sample inside the column. And here are some of the properties we can measure with the IGC system. So we can measure different components of surface energy, like dispersive surface energy and specific surface energy, as well as the surface energy distribution, giving the heterogeneity mapping on the surface. And from the surface energy, we can also calculate the work of cohesion and adhesion between different samples. And if we are using some polar molecules, we can also measure the acid-base properties of the solid materials. And with some different methods, we can then determine the Hansen solubility parameter for the polymers, as well as the diffusion or the phase transition on these samples. And the same here, I will just focus on the sorption isotherms and the BET surface area determination. So IGC as a chromatography technique has a really good reproducibility. And here's an example with a pharmaceutical powder, the paracetamol, with 10 different runs on the same column. So the BET surface area here is between 0.27 to 0.28 square meter per gram, with the RSD less than 2%, showing an excellent reproducibility of IGC measurement. And IGC has a really good accuracy as well. So here's an example with the reference BET standard, the CRM170 sample. So we did the octane sorption at 30 degrees, and here is the sorption isotherm, and this is the converted BET line. So in the reported value for this CRM 170 sample is about 1.01 square meter per gram, and the measured value with IGC method is about 1.05 square meter per gram, showing a good agreement in the literature as well. And apart from accuracy and reproducibility, another advantage of IGC is the system can be equipped with the background humidity controller to study the impact of humidity on the surface properties. For example, here with the CRM 171 sample, at dry condition, the surface area of this sample is about 3 square meters per gram. But with increasing of humidity, you can see that this surface area is dropping to almost half of the original value at 90% RH, which is due to the water molecule competing the size on the surface and blocking the available surface area for the probe molecules. But in case of the cotton study, it shows some different trends. So with the increasing of humidity, the surface area of the cotton is also increased by about 10%, which is probably due to the hydrophilic character of the cotton, that the water makes the fibers swelling and increase the surface area in this case. And another study is about the magnesium stearate. So the surface area of this sample is also decreasing with the increasing humidity. But after drying at 110 degrees, this surface area is becoming even larger than the original surface, which is probably due to the sample change the structure during the preheating process and lose some tightly bound water and change the hydration state as well. So if we measure this sample with the nitrogen method, this probably be the value we will get without the hydration water, but it's not the original surface we want to measure at very beginning. So the case study here with IGC is we measure the surface area with different fibers, and the material we have here is the synthesized fiber, the cellulose fiber, the biomeat, and the other two nitro fiber, the kinetic fiber and the flex fiber. And here are some microscope images of the sample. So for the biomeat and kinetic fiber, the surface is quite neat and clean in the image. But for the flex fiber, it shows some kind of fragments of cuticles on the surface. And here are the BET results for 3 fibers. So each columns were repeated for 3 times, and the standard deviation is less than 5% for all the samples, showing the excellent reproducibility of IGC method. The surface area of these biomeat and kinetic fibers is about 0.5 square meter per gram. It's quite similar, but for the other sample, it's almost 3 times larger than the other 2 samples. And this high surface area of the flex fiber is related to the surface roughness as shown in the previous image as well. And this is the study within the same column. And then we pack different samples in different columns and measure the surface area of different batches. So here shows the 2 best fiber, nitro fiber here, shows a quite high batch-to-batch variation compared to the biomeat fiber is quite small in the variation. And this is expected as the nitro fiber have irregular structures as well as the inhomogeneous properties, while the synthesized fiber is more uniform and more homogeneous in the nature. So this study demonstrates the potential of IGC for the characterization of nitro fibers and also measure the batch variation with a very high sensitivity as well. And this study is published by Dr. Legras and Dr. Konda, and here's the reference paper. So if you're interested, you can have a look in detail later. And the last study here is from the spell group at Imperial College about the freeze-dry biologics. And here we use both nitrogen and IGC to measure the BET surface area of these freeze-dry biological materials. So for the nitrogen methods, it was degassing under vacuum at 30 degrees overnight, and the experiment was done at liquid nitrogen temperature. And in case of IGC experiment, it was preconditioned at 30 degrees with the flow of helium for 2 hours, and the experiment was done at 20 degrees with octane sorption. And both methods use around 100 to 400 milligram samples for the measurement. So here are the BET results. It's also repeating for 3 times on the same column. So as you see that the reproducibility of IGC results is much better compared to the nitrogen sorption. And these smaller surface area, these higher surface RSD value for the nitrogen sorption are likely due to the relatively larger dead volumes within the volumetric instrument, which becomes critical for the lower surface area materials. And here's the summary between the two methods as well. So the advantage of IGC measurement is to run at ambient temperature and pressure. And this is very important in this case for this freeze-dried material to avoid any change in the structure during the BET surface measurement. And it also allows to study the effect of moisture on the stability of this freeze-dried sample as well. And this is the reference paper for this study. So for conclusion, DPS and IGC are two vapor sorption techniques used for the characterization of a wide range of materials, including the pharmaceutical powder, fibers, polymers, or film samples. And by studying the isotherms, we can calculate the BET specific surface area, especially for some very low surface area materials with quite good accuracy and reproducibility. So I hope you will find DPS and IGC useful for your future research. And that's all for my presentation. And thank you very much for listening. So if you have any questions, just let me know. Thank you.
Yeah, thank you, Meishan, for that very informative presentation. We are now open for questions. So if you have questions for Meishan, please use the chat box or unmute your microphone. Shall I ask for the first question, which I got earlier? The question is, what's the difference between the two vapor sorption techniques that you've showed us today?
Okay, that's a good question. So, well, IGC is more focusing on the surface property of the solid sample, but DPS can also measure some bulk property of the solid, like the amorphous content in the material or the vapor-induced phase change. And also in case of concentration, IGC is more accurate to control the very small concentration of probe molecule, especially in some like infinite dilution range. But DPS can go much higher concentration, that it can go up to 98% partial pressure. And also in terms of the BET determination, like IGC is limited by the pulse injection scheme that is more suitable for the low surface area materials, while DPS can also measure the very porous material with high surface area, like 1,000 square meter per gram. And we also have the vacuum system, especially for this kind of application.
Okay, thank you, Meishan. So I have a question here from Rathi. What is the lowest SSA that can be measured on IGC or DVS, and what is the comparison with krypton SSA?
The lowest limitation for IGC could be like it can measure like 0.1 square meter per gram, still with quite good reproducibility. For example, for some higher fibers, it has like 0.1 or 0.2 square meter per gram. I'm not quite sure the comparison with the krypton sorption, because normally we just use the nitrogen sorption. Sorry.
Another question is, how much sample should we use for the DVS and IGC measurements?
Like for DPS, it's a very sensitive technique, so we usually just use less than around like 10 milligram samples to get a faster equilibrium. But we also have different configurations of the balance that will allow us to put more samples for the measurement, like several grams of sample. And in case of IGC, it's depending on different natures of the sample. For example, for the low surface area material, we will use about 100 or 200 milligram samples to get enough interactions. But for some porous material, we just need maybe several milligrams or less than 10 milligrams to reduce the elution time of the peaks.
I have a couple of questions from the chat. For a particular powder sample, if BET is done on same instrument installed at two different places under same conditions, why the data values differ?
If just the same instrument and the same conditions, the results should be quite similar as well. Like the experiment to experiment RSD, we have the technical notes and tells about 2%, and the instrument to instrument RSD is also about 1 to 2%.
Another question is from Musa. Would you explain more on how humidity increases the surface energy in IGC measurements?
Well, it's also depending on different samples. Like for some hydrophilic sample, the humidity will have a large impact on this kind of sample for surface properties like surface area or surface energy. But for some hydrophobic sample, like polyester or polypropylene, maybe this time the humidity will have less impact on the surface property, like the surface area will not change at different humidities, and surface energy may not change as well. So depending on different samples and different natures of the sample.
Is that answer your question, Musab?
It is. Thank you very much.
I saw a different question. What's the limitation of IGC for very high surface area materials? And can I use a column with only 20 milligram? Because IGC is using the pulse injection. So it has a limitation for the BET surface area because we need to cover the whole surface with the probe molecule. So it can measure as high as maybe 100 square meter per gram. But for the surface energy, IGC only use the very finite dilution range, very small concentration. So we can still measure the surface energy of those porous material. So with the porous material, like some active carbon with the surface area about maybe more than 100 square meter per gram, we only need to use about 3 or 4, less than 10 milligram of the sample. So of course we can use the column with only 20 milligram.
Okay. We have another question, Meishan, from Nisha. Is there a trend powder samples follow after pretreatment?
As far as I know, for the nitrogen sorption, the different like preparing method and the preconditioning conditions will give different effect on the final result. And in case of IGC measurements, the preconditioning is in situ before the experiment. So just the flow of the carrier gas, like helium or nitrogen, at a certain temperature. So if this kind of precondition changes the structure, like higher temperature will remove some of the water in the surface. So the longer time will give a more like clean surface, and that will probably affect the surface area at the final result. But if the precondition, the ambient temperature doesn't affect the surface of the material, the result should be the same.
Okay.
I hope this answers your question.
Yes, yeah. Thank you so much. Are there any more questions from our participants? Okay, I think this concludes our presentation today. Thank you so much. If you have further question regarding the presentation, please email us at science@surfacemeasurementsystems.com and we will try to answer your question. For further information about the services that we do and the products that we make, just visit our website or email us. Thank you so much to all participants. Thank you so much, Meishan, for your time today.
Thank you for joining the webinar. Thank you.